Yeah, no problem. Thanks very much for having me, Jonah, and thanks everybody for coming along to listen to me chatting a little bit about parameter estimation and what that means. So this is going to be kind of a whistle-stop tour of parameter estimation. It is a big topic, and I have about half an hour, so I'm going to go through as much stuff as I can, but it is very much going to leave you hoping for more and wanting to go off and read and learn more about the subject, I hope. So, as Jonah says, I'm a postdoctoral researcher at the Institute for Gravitational Research here at the University of Glasgow. So I work mostly on studying compact binary coalescences and mostly binary black hole coalescences. But I used to work in unmodeled source analysis in the past. And I guess I'm here to talk to you largely because I led the O3A, O3B, and O4A parameter estimation analyses. So I did the parameter estimation for most of the last three observing runs of advanced LIGO. So I have now had my fair share of looking at new binary black hole signals. So very quickly, what is parameter estimation? Well, it's a way of getting from a gravitational wave to principally what we look at are the properties of black holes, but also of neutron stars if we're lucky enough to see a neutron star signal. So it's the analysis which goes from getting that data from the gravitational wave detector and working backwards to work out what kind of black hole, what kind of neutron star produced the signal. And it really is one of the foundational analyses that we do as a community, as a collaboration. So most of the astrophysical analyses, which we do based on gravitational waves, rely on us having these parameter estimation results. So rely on us having worked out what those compact objects are that have collided with each other to produce gravitational waves. So you might be thinking, well, is this not kind of what searches are for? And I know you all got a talk yesterday about gravitational wave searches. And those scour through all of the data which we have from the detectors looking for signals in the data. And they give generally a kind of a rough guess of the properties of the signal. But what we do in parameter estimation analyses is to take a much more in-depth look at a very small amount of the data which contains the signal and which is immediately around that signal. So PE analyses are much more detailed, but because they're much more detailed, they're much slower and they take a lot more resources. So we only look at this much smaller quantity of data. We get a lot more information about the system, and because of the way that we do it, we also get an understanding of the uncertainties, the errors in our analyses. So we get error bars on those estimates as well. So just a very quick structure of what this talk is going to be. Most of it is going to be chatting about Bayesian statistics, so the way that we actually perform the parameter estimation. And I will be trying to answer the question of why we can't give you a straight answer about what size any of these black holes are. And we always say that it's between so and so many solar masses and another number of solar masses in size, why all of our answers are probability distributions rather than nice single numbers like you might hope for. Then I'll talk a little bit about what we do in the LIGO-Virgo-Cagra collaboration to actually perform parameter estimation analyses. And I'll give you a very brief overview of what the codes are that we use to do that. I know that some of the rest of the workshop will take you through some tutorials on actually running some of those codes. So I won't labor any of that. I'll just give you a nice overview of what sort of process we do. And then I'll very quickly talk just a couple of slides about how you can access the samples from our analyses, the published analyses, if you want to go off and do any more detailed analysis on those. So Bayesian statistics, I could give a whole lecture course about this, and 20 minutes is not going to allow me to get through very much. But what do I mean by Bayesian statistics and Bayesian inference? Well, Bayesian inference is basically a process where we take information which we already know about a signal. So that might be that we have some prior knowledge of the distribution of black holes in the universe, for example, of neutron stars in the universe, which allow us to say, well, a certain kind of black hole is more likely than another. So if we have seen a signal, it is more likely that we've seen one which is of this mass rather than one which is thousands of times bigger, for example. So we take prior information, prior distributions, prior probability distributions, and we multiply those by something which we call a likelihood. Now, a likelihood is composed of producing the likelihood requires us to take data. So the data in this case being our gravitational wave strain from the detectors, and then some information which goes into a model. And we perform some sort of comparison between a model. In this case, it's something which we call a gravitational waveform. I'm not going to have any great amount of time to talk about what those are or how those work, but we have a model which, depending on the masses, the spins of our black hole or our neutron star, that model is going to change, and we compare it to the data. And the more similar, in effect, that the model looks to the data, the greater this likelihood. So when we multiply these two things together, we get something which is called a posterior distribution. It is normalized by a factor which we call the evidence, but very rarely in parameter estimation do we think an awful lot about that evidence. So it is principally this proportionality, this multiplication of the likelihood and the prior that gives us our posterior distribution. And the posterior distribution from parameter estimation is, in effect, our result. So once we've detected the gravitational wave, we use this parameter estimation process to work backwards to get the properties of the astrophysical system. Part of the reason why we do this Bayesian, take this Bayesian approach, and why we need to have a complicated statistical approach to do this, is that gravitational wave detectors produce data which is very, very noisy. So there will be lots of sources of additional variation within that strain output, within that data output from the gravitational wave detector, which is not produced by black holes and neutron stars colliding. And we need to go through the data and find the bits which are produced by the signal rather than anything else. And that process is what we call matched filtering. So that is how we produce that likelihood. As I said, we compare the data to waveform models, and our waveform models look something like this. So a pure, perfectly detected signal, if there was no noise, would look something like this. So we get this very distinctive morphology of the waveform, which we are then trying to pull out of the data. And the shape of this signal is affected by the masses of, I'm going to talk about black holes for most of this talk. Neutron stars bring in a couple of extra parameters, but principally we're talking about the masses of the objects, the distance that the object is from us on Earth, its position in the sky, and then the spins of the two black holes. There are a variety of other parameters as well, but these are the ones which we're generally most interested in when we come to do an analysis. So those are the things which we vary across the model to compare to the data. So you can see on the left, this is an example of what our data actually looks like, and on the right is that model. So what we are having to go through is data like this. This data contains this signal on the right, but it's very hard to see by eye, and it's relatively difficult to see even when you apply a parameter estimation algorithm to pull out that raw signal. And the case on the left here is, in fact, a very good case. Most of our signals are buried at a much lower signal-to-noise ratio, so they're buried in much more noise than the data in this plot has. So it's a difficult, a reasonably difficult process that we need to go through to do this. So we have this likelihood model and this waveform model. So the waveforms are based on real physics. So as we vary the parameters, there's real physics and general relativity, but we cannot evaluate general relativity directly. So we use various different approximations to that general relativity, and you will come across, both in the literature and in some of our results, references to lots of different approximants. So they all have really quite difficult to remember names, things like IMR phenom XPHM, SEOB and RV5PHM, and it is all a kind of all of the names mean something, but you need to go off and have a look at some of our papers to really understand what the differences between those are. But these models are just try to approximate the physics in slightly different ways. And we tend to look at doing parameter estimation with multiple of these models, so that if there are any discrepancies between them, then we can see these, we get results from both and we can compare them. So we take the waveform model, as I say, we compare it with the data through cross-correlation in effect. So we do something which is we call a noise-weighted inner product. That's just jargon at the moment, but our basically we take into account an estimate of the amount of noise in the data along with our signal to produce that likelihood. We calculate the likelihood with respect to these two things, and then we multiply it by the prior probability, as I said before. And we do this at many, many different sets of parameters for the model. So we will change all of the different parameters across the model, work out what that posterior probability is many, many times. So producing an entire analysis will frequently require us to evaluate the likelihood hundreds of thousands or millions of times. And we do that with something called a stochastic sampling algorithm, so you will have encountered things like Markov chain Monte Carlo, which is one of these stochastic sampling methods. Popular implementations of this include PyMC, Pyro, and MC. So those are just, in this case, all three of those are Python packages which allow us to do Markov chain Monte Carlo explorations of this likelihood of this posterior probability distribution. What we tend to use in gravitational wave studies and in what we do in LIGO, Virgo, Cagra is we use something called nested sampling. Now, nested sampling is conceptually similar to what Markov chain Monte Carlo is doing. It is randomly sampling that posterior in a way which is somewhat principled. I'm not going to get into talking exactly about how the samplers work, but they are designed to explore the parameter space and look for features within that posterior probability distribution, including, for example, peaks in it, which represent that there are represent the most likely, for example, sets of parameters. So the one which we tend to use in LIGO, Virgo, Cagra is one called Dynasty, but there are a variety of other implementations of nested sampling as well. So the advantage that we get of nested sampling over MCMC is that it also gives us this constant of proportionality, which this evidence, and this allows us to compare different models. However, that is a slightly more advanced aspect of parameter estimation than what we need simply to understand the underlying physics of what produced the signal. So once we've done all of this sampling and we've got many iterations of this, many evaluations of this posterior probability distribution, we end up with what we call posterior probability distribution samples. And those are the things which ultimately compose our result. So this gives us, these are samples from a probability distribution. And when you see things in our publications like GW, the gravitational wave transient catalogs, the results in those are calculated from those samples. So we will produce things like we will quote things like the median of those samples from the probability distribution, and then calculate confidence intervals, for example, based on those, which gives you your error bar on each probability, on each quantity that you're analyzing. The samples themselves, I appreciate this is a completely impossible to understand plot. There is no way that I can put this onto a single slide. What we love in parameter estimation are these things called corner plots. What this is a representation of the posterior probability distribution, where we show each of the pairs of parameters which are in that probability distribution, and we show the joint marginal distribution of those. So basically, we show how various different parameters correlate. So as you go through some tutorials for tools like Bilby, which is one of our parameter estimation tools, you will come across results plots which look a little bit like this. And then on the diagonal on this, you get something which looks a lot more like a conventional probability distribution represented as a histogram. And those are sort of where our estimates, where our quotations of the various different quantities for that system come from. So something which maybe looks a little bit more familiar, and this looks a lot more like the sort of thing which we get in our publications, in our papers, are these nice little marginal histograms of each quantity now. I have, in preparing this slide, cut off the labels for each plot, but what we've got here are things like chart mass, mass ratio, various different representations of the spin. So you can see that we get all of these little probability distributions for each event. And then this allows us to both work out something like the median, probability, the confidence intervals, but then also see what the structure of that underlying probability distribution looks like. So you can see in some cases that we get something which looks a bit like multimodality, which might be telling us either something about interesting physics in the signal, interesting problems with the data going into the signal, or problems with the model as well. There are lots of different things which might be going on in some of these cases, but we get what you will see when you look through things like GWTC3, our most recent results paper, are big pages and pages of these plots, and these are what our results fundamentally look like in gravitational waves. We don't just rely on giving single number answers, we give you these nice little probability distributions, which tell you all about our confidence in the results themselves. So I then said, I promised I would talk a little bit about how we do things in LIGO. Now, the whole process of analyzing data in LIGO is relatively complicated. I've tried to summarize it in one nice diagram, which I think looks moderately terrifying, and I find it slightly terrifying when I put it all in one diagram. This is sort of end-to-end, where all of how our data comes in on the left from our detectors and ends up on the right as the results which we produce. I'm only going to talk about the stuff right at the end. So really how we go from having the outputs of our searches, so the event list. So the searches give us a list of times where they think that the gravitational wave events have been detected. And then we perform parameter estimation, this detailed analysis on data immediately around those event times. So most of what I'm going to talk about are how those parameter estimation processes themselves, what those look like, but we also have to estimate the amount of noise. So I said that this matched filtering process, this noise-weighted inner product, requires us to have some measure of the amount of noise in the data, so what is not the signal. And we have a specific tool which we use to do that. So I'm going to talk about BaseWave, the tool which does this, Bilby, which is the most widely used of our parameter estimation codes at the moment, and then how we do the post-processing, so how we actually produce the results. There are many, many other parameter estimation codes, which I'm not going to have time to talk about, but some of those are produced by scientists within the LVK, and then some are produced by our collaborators outside of the LVK in the broader astronomical community. So there are many, many options and many different approaches to actually doing this, but Bilby is the one which we have used to produce the last few catalogs. So that's what I'm going to talk about briefly. So BaseWave is the first of these codes. So this is the one which I say is used primarily to analyze the noise component of our data. I think I suspect the tutorials in the workshop don't really touch very much on this. You will either produce PSDs a slightly simpler way, or you'll be provided with PSDs depending what job you're doing precisely. But in our data releases, we provide estimates of the noise, things that we call power spectral density, PSDs, which are produced by BaseWave. So this is an essential component of the likelihood function. And without this, we would not be able to perform the rest of the analysis. So BaseWave is kind of the first step which we need to take in any of these analyses, that we pass the data through to this, and BaseWave estimates the amount of noise which is in that data, which is not signal. The next step is this tool called Bilby. So Bilby is one of the main analysis codes used in the LIGO Virgo Cagra collaborations. And it's designed to be flexible and easy to use. So there are lots of different ways of performing analysis through this, and it can run with many different waveform models. So I can choose to run Bilby analyses with 2, 3, 4 different types of waveform, so that I can then compare them later on. So Bilby is also quite nice if you are coming from a Python background, because it is nice and easy to extend with new features, because it is written almost entirely in Python. Some bits of it are written in C or in Cython, just for performance and speed, but the majority of the code which handles setting up the analyses and running things is written in Python. So it's nice, and if you have an idea of how you want to extend parameter estimation or how you want to try some new kind of analysis, Bilby makes it quite easy to go in and do that. Then our final step is a step which uses a tool we call PE Summary. So PE Summary takes on the post-processing of all of the results which come out of Bilby. So I said that what we principally do is perform this analysis by changing different aspects of our waveform model, things like the spin and the masses of the two objects. Frequently, what we in fact want for better astrophysical understanding are combinations of those parameters, or we want to reparameterize those results in some way. So one of the things which PE Summary does is it will take the results in their raw format out of Bilby, and it can do all of these reparameterizations. And then it's a very helpful tool because it can produce summary plots of all of these different parameters, all of this different data, in order to give us the kind of results that we want to look at, and we can have a look through this and see, is our parameter estimation showing us anything interesting? Oftentimes we want to look through it to see, did something go wrong during the process of parameter estimation? So did our, for example, does it look as though we chose inappropriate prior distributions on our analysis is a frequent thing that we'll look at. But it produces these very nice web pages full of summary plots for us to go look at. And then, as I say, yeah, it produces these derived parameters, so things which are produced by combinations of different measured parameters. So PE Summary also produces the final data files, which we release, which the LVK releases to the general public in a consistent format, which brings me nicely onto the last thing which I want to talk about, which is really how you can go about using our data. So you'll learn during this session and during the tutorials about how you can actually set up these parameter estimation runs. But a lot of the analyses which we have done for publication will take many days to run on really quite expensive compute resources. So it is often going to be more viable to go back and use the results which we've published. Of course, we also provide all of the information which you need to redo any of these analyses if you want to, and if you have access to the appropriate resources. But it is hopefully convenient to go back and get those samples. So these are available through the Gravitational Wave Open Science Center, GWOSC, and they're also archived on Zenodo. I've put a link in the slides to the results from GWTC 3.0, so the most recent results. But when we start publishing the results from the 04 runs, for example, these will come out in the same format, and we have results from the first 3 observing runs, all available in this kind of format. So the samples come in this HDF5 based format, which PE Summary produces, and as well as posterior samples. The posterior samples which we produced during parameter estimation, we release things like prior samples, so samples evaluated directly from that prior distribution at the various points in parameter space where we've evaluated the posterior, along with all of the configuration data that you need to reproduce the analysis, the power spectral densities, the PSDs, that estimate of the noise, and various other things which go into producing one of our parameter estimation runs. So I realize I've given really quite a rapid introduction to parameter estimation, but Jonah, I think is the time. I'm assuming there's time for questions. I've gone through this a couple of minutes faster than I was anticipating. So